Okay, so today we're going to review some of the vocabulary we discussed in our unit on circles, and we're going to show you why we discussed circles right before starting trig. Most people do not realize that the heart of trigonometry is a circle, not a right triangle. We've always been taught how to use trig on a right triangle, and that's where we're going to get in a few days. But the heart of everything comes from these circles we've been talking about. You recall there were some features of a circle, some interactions between lines in the circle that had special names. One of them was a secant. A secant was a line that cut through a circle. It contained a chord. The chord was the part of the secant that was internal of the circle, inside the circle. One definition of a chord is it's just a line segment that connects any 2 points on the circle. But the more technical definition of a chord is it's a portion of a secant that is inside of the circle. Then we had, if I can draw it right, a tangent. Remember, a tangent was a line that just touched the surface of the circle, but never actually cut into it or penetrated the circle in any way. We had some special rules for tangents that we discussed, where if we had two tangents, the portion of the tangent, or the portion of that line that's between the point of tangency and the intersection of those two tangents, in other words, this length here, which of course would also be this length. Oops. That didn't work well. Let's try that again. It should also be this length here, if that's the point of tangency, would be the same length. So when we're looking at tangents, that's one of the things we look at. One of the important features of them is the distance or the length between that point of tangency and the intersection between some other feature. That'll be important coming up. Something we mentioned briefly and we didn't really dwell on. Well, something we mentioned a lot, of course, was the diameter of a circle. But I mentioned something called a reference diameter. The diameter was nothing more than a chord of the circle, a segment that connected 2 points on the circle, that also contained the center of that circle. Now, it's not really necessary that I go in that technical definition because you've all talked about diameter since about the second grade, so you know what it is. But it's very important that we define a reference diameter. A reference diameter is a horizontal diameter. Now we mentioned a little bit, pretend that's horizontal, I didn't get it quite straight. We mentioned a little bit when we were talking about angles, about navigation, how navigation fell into the whole idea of how angles were defined, difference in direction and stuff like that. The reference diameter also comes from navigation. It is the east to west diameter. And most of your navigation would be, if you wanted to define a direction, you would define, if you're heading in this direction here, that might be defined as 28 degrees or however many degrees south of east. It's always from the east and the west, never from the north and the south. Those were defined. So that's why that is called the reference diameter. With that in mind, then, another feature we discussed was something called a sine. Does anybody remember what the sine was? We have to have a reference diameter to define the sine. And a sine is a dimension or a property of each point on the circle. For example, if I pick a point right here, the sine of that point is the segment that connects that point to the reference diameter, always connecting at a perpendicular, at a right angle. Technically, the sine is actually the distance from that point to the reference diameter. And distance in geometry is always measured at a perpendicular. So now some of these words might be sounding familiar. Sine, tangent, secant might not be quite as familiar for those of you that have had trig. So the question is, how does this all tie in? First of all, when we're talking about circles in trig, We're talking about something called a unit circle. A unit circle is nothing more than a circle with a radius equal to 1 unit. What unit is it? Doesn't matter. 1 inch, 1 centimeter, 1 astronomical unit, 1 atomic unit, whatever. It doesn't matter what that length is. It is just 1 unit of whatever unit you choose to use. So, let me create a circle here. Let's pretend that this is a unit circle, which means its radius is 1. If I put in a reference diameter across here, what is its diameter? 2. Very good. So it's 2 units. Now there are other features of this circle that we'll discuss eventually, like the circumference and stuff like that is also going to be defined in terms of units. But for now, let's bring in some of this vocabulary. So we have our reference diameter. To locate a point on the surface or on the edge of the unit circle, again, referring back to that idea of navigation, this point out here on the circle would be defined by this angle here that produced the segment that went in the direction of that point. That the location of this point is its direction from the reference diameter. Now, in order to make things a little bit simpler, I'm also going to draw in a vertical diameter. This is not a reference diameter in the purest sense of the word, but it will get used as a reference diameter in some of our trig functions that we're going to look at. So we've located this point right here by defining its direction. This angle here can be defined, I could give you a number if I wanted to. I could say, 29 degrees or 37 or whatever number I wanted to put on it. For right now, I'm not going to do that. We're going to define it with a variable. I could call it x, y, a, b, c, whatever. For right now, though, it's time to start learning a little bit of vocabulary or symbology, math symbology. I'm going to call it theta. What I just drew in there, draw it a little bigger for you, looks like this. Kind of like an O with a line through it. That is the Greek letter pronounced theta. In math, especially in trig, we tend to label the variables that we use to label angles, we tend to use Greek letters. Theta, phi is another one we'll use. Alpha, beta, gamma. Don't worry, I'm not going to try to teach you the Greek alphabet. It's just you're going to see these symbols up there. They look weird. Alpha kind of looks like a fish, but that's all they are. They're just variables, just like X, Y, Z, or A, B, C. It's just that's kind of a convention. A lot of the packets I use will actually just use A, B, and C, which will make it a little easier for you. I'm just putting this out there because that's what I am used to, so you'll see me fall into it because that's how I was taught. But anyway, now that we've defined this angle here, theta, the trig functions are now features of this point here on the circle, this red dot. And the easiest one to define is the last one we discussed, the sine of that point on the circle is that length. So the sine of that angle theta is that distance from that point on the circle, bless you, down to our reference diameter. The abbreviation, of course, is usually sin theta, or sin A or B, whatever angle we're looking at. So sine is our first major trig function, first of our main trig functions. Now the next one you've probably heard of, tangent. Remember, tangent is touching a circle. The problem is tangent to where? Well, when we're talking about the unit circle, the tangent is always tangent to the unit circle at the reference diameter. So it's going to be tangent right there at that brown point. So now the next question is, where does it end? Well, I mentioned that when we look at tangents, it's always, the important feature is always the distance between the point of tangency and where it intersects some other feature. So let's expand on that a little bit. If I expand this line here that goes from the center out to our point like this, of course it can go on forever like that if we wanted it to. That line, by the way, cuts through the circle, which means it is a secant. Very good. Our tangent, I'm going to go back to my brown, goes from that point of tangency there at the reference diameter to where it intersects the secant. That length there is the tangent of angle theta. Again, usually abbreviated TAN of theta. And you might have guessed by now the distance from the center of the circle to where that tangent line intersects the secant. That length is the secant of our angle theta, often abbreviated SEC theta. So our other two main trig functions, we mentioned the tangent and we mentioned the secant. Those are our three basic trig functions. Now, which one have you heard a lot of that is not on my list right now? Cosine. Very good. Most textbooks teach sine, tangent, and cosine as the three main trig functions. In fact, if you look at your calculator, the three buttons that are on your calculator are sine, cosine, and tangent. Where did the cosine come from in all of this? Cosine is technically not a word. Cosine is a word with a prefix. You'll probably recognize the word sine in there. So what we're looking at is the prefix co, and what does that mean? Co comes from the word complement. When we're talking about angles in geometry, what does the word complement mean? Yeah, add up to 90. The prefix co then means of the complement. So the word cosine means the sine of the complement. So let's break this down. Let's say I ask you to find the cosine of 30 degrees. What that is asking us to do, looking at our unit circle still, pretend that looks like a circle. I'm going to try to draw it a little bit better. We have a reference diameter. 20 degrees, of course, would be something like that, right? Or not 20, 30. But actually, look at what I'm doing, sorry. 30 degrees would be something like that. Well, the sine of 30 degrees, remember the 30 degrees, all that's doing is locating this point on our circle. The sine of 30 degrees is that right there, that distance. But we don't want the sine, we want the cosine. Remember I said I put in this vertical diameter here? It's not really a reference diameter, but it gets used as one. Because if this angle right here is 30 degrees, where's the complement of 30 degrees? Right there, you got it. Off of that vertical diameter, from the north direction if you want to look at it that way. That is 60 degrees, or the complement of 30. So if we're looking at that angle, and now switching our reference so that this is our reference diameter, where would the sine of that angle be? from right here to right there. That is the cosine of 30 degrees. Now, one thing you'll notice here, it's the cosine of 30 degrees, but it's also the, exactly, the sine of 60 degrees. What special relationship do 30 and 60 have? They're complements. They add up to 90 degrees. Very good. The definition of cosine is the sine of the complement. Therefore, the cosine of an angle is equal to the sine of the complement. I know you have a cosine button on your calculator, but if you didn't have a cosine button on your calculator, if you wanted to find the sine of 23 degrees, or sorry, not the sine, sorry. If you wanted to find the cosine of 22 degrees, all you'd have to do is find the sine of 67 degrees, the sine of its complement. They will be exactly the same. In fact, if you want to pull out your calculator for a second, punch that in and test it for me. Cosine 23. Now, most of you, when you hit the cosine button, you're going to get that parentheses that shows up. As long as you're just doing the simple cosine of an angle, it won't make a difference. If you're doing anything more fancy, a lot of times you will have to close the parentheses, but for now you don't have to worry about closing it for just an angle. Did you get 0.9205 or something different? Okay, good. In your calculators, there's something called the mode you have to check. Hit the mode button. Now you'll see on mine here, mine's got a little bit different display, but right here you see it says degrees is highlighted, and over here is radians. Generally, if you're getting the wrong number when you do a trig function, it's because most calculators come out of the box preset to radians. And we'll talk about what radians are sometime in this week, probably. For right now, though, you need to set your calculator to degrees. So see if you can figure out how to do that. If you can't, let me know and I'll come take a look at it. But if it's not set to degrees, a lot of the stuff you're going to do is going to be...
So wait, what are we supposed to plug into it first to see if it's wrong?
Let me get out of here. You do the cosine of 23, you should get 0.9205. So when you did the cosine of 23, you got 0.9205. Punch in the sine of 67. Hopefully you get 0.9205. If all goes well. Everybody good? Cool. So how does all of this mess... By the way, that also defines that if that's a cosine, and if we extend this out, we end up defining a cotangent would be, using this as the reference diameter, would be from this point of tangency out here. That would be a cotangent. And a cosecant would be from the center out to that intersection as well. So all those features, cosine, cosecant, cotangent, every trig function has a what we call a cofunction, which is just defining from the complement of that angle. So anyway, let's now take a look at just this special little right triangle that's formed here. I'm going to redraw this again. Pretend that looks round again. So I'm going to put in the reference diameter and the north-south diameter, or the vertical diameter, every time I do the unit circle from now on, just because it's easier if that unit circle is divided into what we call quadrants. We talked about quadrants briefly when we did the XY graphing last semester. Now, this is our first quadrant, second quadrant, third, and fourth. And for the most part, the important quadrant is quadrant number 1 here, because we tend to work with angles between 0 and 90 degrees. We'll look at some angles bigger than 90 degrees, but even then, we tend not to go above 180 degrees for the most part because it's impossible to have a triangle with an angle bigger than 180 degrees because the angle sum is 180. And most of what we use trig for applies to triangles. It is, however, possible to do trig functions of angles pretty much up to infinity. You can use negative angles, positive angles, because if you think about it, if an angle starts on this, it can wrap around as many times as it wants to. It's cyclical, however, because once it gets to 360 degrees, you're basically back at zero. So 361 degrees and 1 degree are in exactly the same spot. So if I have, let's say this here, this point that's defined by a 10-degree angle, we really don't know for sure if that's at 10 degrees or 370 degrees or 730 degrees or whatever. The key is it doesn't matter because all that matters to define our trig functions is the distance from that point to here if we're looking at sines, or from that down if we're looking at tangents or whatever. So anyway, so we only really need to worry about trig functions from 0 to 360, and as I said, in practice, 0 to 180. The angles that are bigger than 180 degrees, they come in, we start talking about harmonic motion, bless you. Electricity, especially like an electric motor, is basically harmonic motion. It's a cyclical motion. Or we're talking about a spring or a pendulum where it moves back and forth at a regular rate. The location of something like that is defined by a trig function, a sine usually, or a cosine. The electricity. Electric motors do not put out a constant voltage or a constant current. It goes up and down. The power coming out of our outlets, what's called AC power, alternating current power. That is defined by one of our trig functions. And of course, it doesn't just go one cycle or 360 degrees and stops, it keeps going. So that's why we do have angles bigger than 360 degrees that we use. So anyway, let's draw a generic angle on here again. Here's my angle theta. The sine of theta is this distance right here, of course. I'll put it out here. Now we said the cosine of theta came from this distance here, because this would be the complement of theta over here. Technical symbol for complement is the variable for the angle with a little line above it. That means complement. That's not a symbol that any of the paperwork or the books that we use in this class use. I'm just throwing it up there because I don't want to write out the word complement right now. Anyway, that's the cosine of theta. Well, where else on this unit circle and within that triangle that we defined here, do we see that same dimension? Right. There we go. That right there. So rather than having to go up here and define the cosine, we can define the cosine of our angle right down here as the bottom or the base of that triangle. So I'm going to take that symbol out of there because we don't really need it. And then, of course, we can keep going, extending this out here just a little ways. Here is our tangent right there. So I'm going to put that in a different color so we don't confuse it with our sine. So that feature, of course, that's going to be a right angle there because that tangent is touching the radius of the diameter, and it always forms a right angle with the radius at the point of tangency. So that'll be the tangent of my angle. And if I want to go that far, I know secant used to be one of the main trig functions, and now it's kind of faded. The secant of our angle is right up there. How did we get to our basic definitions that we use for trig functions? And that's where I want to get before we end today, is I want to come up with the basic triangular definition of trig functions that you're more used to seeing rather than the features of the circle. So let's take this little highlighted triangle that I have right there. On this triangle that I highlighted, I'm going to redraw it down here. Here's the angle that I call theta this length on this side was the sine of that angle. This length down here was the cosine of that angle. Do I know the length of the hypotenuse here? Yeah, what is it? Remember, what's the name of this circle? Unit circle, which means the radius of the circle is 1 unit. That hypotenuse of our triangle there is a radius of the circle, which means its length is 1 unit. Very good. So that is a length of 1 there. So we have a little triangle here. If I now want to, trigonometry is about ratios. We spend a lot of time talking about similar figures and similar triangles and the ratios and the proportions that define them. Well, if I have another triangle over here, first of all, it's a right triangle. And if it has the same angle theta right here, at this point, I know that these two triangles are similar. What was the definition of similar triangles? Well, one definition we used was that the triangles are enlargements or reductions of each other. The other definition to test to see if they were similar, remember they had to have all three of the same angles. But if two of the angles are the same, because we have theta and we have a right angle, the third angle has to be the same because all triangles add up to 180 degrees. So by knowing that it's a right triangle and by knowing that they have the one angle in common, angle theta, we know they're similar. And what trig is about is comparing these right triangles to this triangle from the unit circle that has the same angle theta. So on this right triangle here, we have the hypotenuse. The hypotenuse is the side, of course, that doesn't touch either of the right angles. We've talked about that a lot before. The other two sides are called legs. But now it's going to be important for us to differentiate between those two legs. Those legs are defined or differentiated by their relationship to our angle theta. Now, if we're looking at this angle, this is the angle we're concentrating on, the definition will be different than if we were concentrating on this angle. It is possible to use this angle to do our trig calculations. If that were the case, then the names of the legs would be changed according to that angle. So anyway, if we're using this angle, this leg here touches that angle. In geometry, we have a name for things that touch. Tangent is kind of a name, but there's another name that just means touching and not in any special way. That is adjacent. Adjacent means touching or next to. That is the adjacent leg because it touches or it is next to the angle of interest, the angle that we are looking at. This side, this leg over here, does not touch it in any way. In fact, if you're going to describe its location according to this angle over here, you might call it a cross or opposite. Very good. It is the opposite leg because it is across from or opposite of the angle that we are looking at. I'm going to abbreviate these just to make it easier. Opposite, adjacent, hypotenuse. So if I wanted to define the sine of angle theta, this length from this triangle is its sine. Well, how can I define that sine if all the information I have is this triangle here? I'm going to use similar triangles. Assuming I know these lengths, the opposite, the adjacent, the opposite, and the hypotenuse, if I have those sides of that triangle, I can then define my sine. I can find this length, again, using similar triangles. I start always with the two sides that correspond from the triangles that I know the length of. Well, the only side here that I know the length of right now is the hypotenuse, 1. So the hypotenuse of this triangle matches up with the hypotenuse of unit 1 from our triangle from the unit circle. Well, I want to know the length of this side right here, the sine. Is that going to go on top or bottom? It goes on bottom because it's from the same triangle as the 1, right? Sine. What side in the other triangle matches up with the sine? The opposite leg. So right now this looks like kind of a jumbled mess, but if I wanted to solve for the sine, we would cross multiply and divide, right? 1 times the opposite would just be the opposite. The sine of theta. 1 times opposite is opposite, then divided by hypotenuse. Opposite divided by hypotenuse. You've probably heard that definition before. The sine of an angle is the length of the opposite side divided by the length of the hypotenuse. Make sense? Where do all the other trig functions come from? Well, we're at it. We could use the same proportion here to define the cosine. The hypotenuse and 1 are linked together here. So the hypotenuse corresponds to 1 again. Cosine is going to go down here. What side in the other triangle corresponds to the cosine? The adjacent leg. So the adjacent there. If we cross multiply and divide, our cosine is equal to 1 times adjacent, is just the adjacent, divided by the hypotenuse. So the cosine of an angle is the length of the adjacent side divided by the length of the hypotenuse. Tangent does not appear on this triangle anywhere, does it? So to find the tangent, we're going to have to look at another triangle. Tangent is part of this larger triangle out here. Let me draw that one out now to deal with. This is the tangent. This is theta again. This is the tangent of theta out here. This, if you recall from the circle, was the secant of the angle. What's the length of this part right here? 1. That is a radius. If we go back up here, that's this piece right here, which is a radius of that circle. So it has a length of 1. So now if we're looking at any other generic triangle, notice it doesn't matter whether I draw the triangle bigger or smaller than the one from the unit circle. It doesn't matter. Looking at this triangle, this is still the adjacent side to that angle. This is still the opposite side, and this is still the hypotenuse. If I am looking to find the tangent, however, the side that I know the length of is no longer the hypotenuse of this triangle from the unit circle. This is the side that I know. That's the one. What side from the other triangle matches up with it? The adjacent. So if I'm looking for tangent, that goes with the 1. So tangent will go here. What's going to go down here? The tangent matches up with the opposite side. So if I do the cross multiplying here, it'll be 1 times opposite divided by adjacent. Which means the tangent of that angle is opposite. Length of the opposite side divided by the length of the adjacent side. While we're at it, let's define secant just for fun. We still have 1 over the adjacent side. Those are the 2 lengths that go together. The 1 and the adjacent side. The secant, however, is up here. So putting the secant of theta, what side matches up with the secant? Hypotenuse. So if we cross multiply and divide to solve for secant there, 1 times hypotenuse is hypotenuse divided by the adjacent. So let's list all these out. I know we've put a lot of junk up here. Let's list this out now in terms of a simple right triangle. So here's our right triangle. Here's the angle we're interested in. Again, we'll label this. The hypotenuse is always the easy one to find. This is which side? The opposite leg. This is adjacent leg. So the sine of that angle was defined to be length of the opposite leg divided by length of the hypotenuse. The cosine was defined to be length of the adjacent over length of the hypotenuse. Tangent was opposite over adjacent. And secant, oops, I got the theta here, was defined to be hypotenuse over adjacent. We didn't go through these with the triangles, but I'm just going to put them out there. Cosecant, abbreviated CSC, that is defined to be the hypotenuse over the opposite side. And cotangent, COT, is defined to be the adjacent side over the opposite side. Now there are some relationships here that we're going to point out in a minute, but for right now I want to put some numbers to this because I've talked an awful lot using just vocabulary and symbols. So let's take a triangle here. Here's our angle theta. And let's say this side is 8 units, this is 15 units, and the hypotenuse is 17 units. If I ask you to find the sine of theta, what would it be? Well, what's the definition of sine? Opposite and hypotenuse. So if I look at this triangle, here's my angle theta. What is the opposite side? 8. What's the hypotenuse? 17. So 8 over 17 is the sine. If you wanted to leave it as 8 over 17, that's perfectly acceptable. Of course, your calculator is going to think of it as a decimal, so 8 divided by 17 is 0.4706. Standard when dealing with trig is usually to round to 4 decimal places, at least with the trig function itself. How about the cosine? Well, for cosine, what's our definition? It's the adjacent in the hypotenuse. Very good. So on this triangle, what's the adjacent side? 15, and the hypotenuse is 17. So again, you could leave it as 15 over 17, or 15 divided by 17, 0.8824 to be the cosine. The tangent would be, well, tangent is defined to be as opposite over adjacent. Very good. By the way, this little list that I put up here, these 6 trig functions, you might want to write that on the back cover of your notebook or make a note sheet somewhere that you keep handy. We're going to need those a lot, and in a lot of the stuff we do, it's going to be really handy to have those definitions in front of you so you can just pick them out and use them. So tangent is opposite and adjacent. The opposite side is 8. The adjacent side is 15. So again, you could leave it as 8 over 15, or you could divide it out to get 0.5333. And for fun, what if we talked about the secant of theta? Secant is hypotenuse over adjacent. So hypotenuse is 17, the adjacent is 15. 17 divided by 15 is 1.1333. So you can get these trig functions right off of the triangle. Now, one thing I want to point out, back up here. Let's look at the secant and its definition. Hypotenuse divided by adjacent. Do we see any other trig function that's similar to that? Well, the cosine is the adjacent divided by the hypotenuse. They're reciprocals of each other, just flipped over. So one definition of secant is it is the reciprocal of the cosine. 1 divided by the cosine. If you look at this down here, if you take the cosine, which is 0.8824, if I do 1 divided by that, now again, there's round off error there, so this might not be exact. But should come out really close, and it does, 1.1333, which is the secant of that angle. So we're going to talk about secants, cosecants, and cotangents. And we're going to be able to calculate them on our calculator. But we're going to need definitions like that, like we just mentioned, to find the secant of the angle. You have to use the fact that it is the reciprocal of the cosine. We'll get to that as we get into these things a little bit more. For now, let's look at a triangle. Let's get back here. Really similar to the one we just looked at. See the similarities yet? Okay. So why am I bothering to put the same triangle up there? What's different? Yeah. This is the angle I'm looking at now. This is still the hypotenuse. The hypotenuse will never change. But what has changed is this is no longer the opposite side. It is the adjacent side because it's next to the angle we're looking at. So many times we get in a rut of thinking this is always the angle we're looking at, and it's not. So then, of course, this is the opposite side. So sine of our angle is, we're not going to divide it out. Just give me the two numbers. Perfect. Opposite over hypotenuse, 15 over 17. Cosine of the angle, 8 over 17. Adjacent over hypotenuse. Tangent, 15 over 8. Opposite over adjacent. If you go back over here, you'll notice in the fractions, this tangent and this tangent are reciprocals of each other. Think about it. If I'm comparing this angle and this angle here, what's the relationship between those two? This is 90 degrees, and a triangle adds up to 180, so these two must add up to 90. They're complements. So what that means is in any triangle, or any right triangle, I should say, if this is angle A and this is angle B, if I know the sine of angle A, let's just throw a number out there. First of all, the sine is always going to be between 0 and 1. So let's just put 0.7324 is the sine of that angle, of angle A. Any guesses what the cosine of angle B is going to be? 0.7324. Because A plus B adds up to 90 degrees. They're complements. Because they're complements, the sine of one has to equal the cosine of the other. So we can find sine, cosine, tangent, secant, cosecant, cotangent from the sides of a right triangle using these definitions here. Any of you that did not get these all written down while you were here? Anybody need a second to get them all written down right now? Everybody's good? Okay. Make sure you have those in the notes somewhere where you can get to them really easily. Well, the next step is, what if, rather than having the sides of the triangle, what if we're just told that this is a 37-degree angle here? Yeah, if I want to find the sine of 37 degrees, we're going to the calculator and we're punching in. Most of you have a calculator that has forward logic, which means you type in sine first and then the 37, like mine. I hit the sine key, 37, and hit equals, and it's 0.6018. I don't think any of you have an old one-line display in here, but if you did have a one-line display calculator, you have to do it just backwards of that. You type in the 37 first and then hit the sine key, and it pops up. So I want you to find now the cosine of 37 degrees. Type that in. What's it come up? 7986. Perfect. 7986. Tangent to 37 degrees. $7,536 if you round it. Okay. Well, time to test you a little bit. Secant to 37 degrees. We mentioned it. Close. It's related to it. It's 1. Remember, secant is the reciprocal of the cosine. So 1 divided by the cosine. So 1 divided by cosine of 37. There we go, 1.2521. Now remember, this number was rounded, so you could put that in. I did this. Now, technically, a better way to do it, you guys have this key right here, x negative 1. That's a reciprocal key. So the best way to do it on your calculator, and the reason I'm showing you this is because when we do what we call inverse trig functions in a couple of days, it's going to be a lot easier if we do it this way. You do cosine 37, and you close the parentheses. That's going to give you the cosine of 37 degrees. Then you hit the x negative 1 key like that. And it gives you the 1.2521. So if you can remember, you either have that x negative 1 key. Actually, most of your calculators looking around the room have the x negative 1 key. Some of them have a key that's a 1 over x like this. That's totally different. Yep. Here, let me come take a look at your. But let's just take a look at cosecant of 37. Secant's the reciprocal of cosine. Cosecant is the reciprocal of sine. So again, what I'm going to do is I'm going to do sine of 37. Close my parentheses, and I'm going to use that reciprocal key. And there it is, 1.6616. We can do the cotangent to 37 degrees, which is going to be the reciprocal of the tangent. Let's take a peek, see if it is. So I'm going to do tangent 37, close. That sounds about right. 1.3270, you've got it. We'll get to that in the next couple days. Yep. I'm going to give you a new packet here, and in this packet, page 338, oops, 341, you're going to be looking at numbers 1 through 53. Very repetitive. You're just going to be punching them into the calculator in some cases to get the function, or you're going to be looking at the sides of the triangle and plugging them in the right spot in your little formula. So as always, do a few of them, skip ahead to some of the more difficult ones. I'll get this packet out to you right now.